All right, here we go. Kinesiology 230, Chapter 3. This is presentation number 9 out of 10, talking energy production and capacity. And we're going to dip back into a few topics from before, but I want to get across, get myself out of the way there so we can go over this. All three energy systems are active at any given time. However, the extent to which each is used depends primarily on the intensity of the activity and secondarily on its duration. So I hope you're sitting here right now thinking through the one presentation where we had the shot putter, the 800-meter runners, and then the distance runners. And you look at that and go, okay, that's the phosphagen system. Cool, got it. Glycolytic, got it. And then you have the oxidative system, got it. And then you start to think of it in terms of, okay, the shot putter is very short-term, explosive, etc. Then the middle are the 800-meter runners, which is kind of like a middle ground, if you will, about 120 seconds. And then all the way over to the right were our distance runners. So the book, and I hope you have that right, because we're going to go over it right here. The phosphagen energy system primarily supplies ATP for high-intensity activities of short duration. That's our shot putter. Those are our sprinters. The glycolytic system for moderate to high intensity. Those are 800-meter runners. And then you have the oxidative system, for low-intensity activities of long duration, which I would challenge you to ask any distance runner who competed in cross-country, and they will tell you that's probably not the lowest of intensity activities, but it's a longer duration, so we can make that argument there. All right, so the book notes this, and they talk about this, and they talk about power output, and they talk about physical work, and I don't want to confuse this with like the idea of work, pushing a boulder across the floor, work, pushing a boulder up the hill is work. But if I ask you to do it in a in a shorter amount of time, that becomes more power oriented. So I don't want you to get confused on this, and I just want to highlight that because it's easy to kind of get lost on that. And the book reiterates here when they start talking about it, the fact that at no time does any single energy system provide a complete supply of energy. There's upregulation and downregulation. Matter of fact, you might think back to the one slide we had where we had the overlap of the bar, where you had the phosphagen system overlapped with the glycolytic system, and there's like a handoff between. Even in that context, when we were comparing the phosphagen and the glycolytic, the oxidative system is still there. It's still operating, but it's just down-regulated in those more explosive, shorter duration activities. Now, this will absolutely be a test question, and it's a brain bender, and it's just silly, but I know it's a test question. I want to go over it. When you look at like the rate and capacity of ATP production, 1 is fastest or greatest, and then 5 is slowest or least. So the rate of ATP production, is fastest based off of 1, and it's the slowest or least when it's number 5. So they're inferring here that the phosphagen system has the fastest or greatest rate of ATP production, but its capacity to make ATP is low. And we know that because there isn't oxygen involved and it can't go into the Krebs cycle, it becomes pyruvate. And the pyruvate itself becomes lactate, and the lactate then, et cetera, et cetera. But if we look at the oxidative side of it, we know oxidation, that infers oxygen. There's an oxygen-related process there, whether it's carbohydrates or protein. Let's go with the proteins who are on the opposite end of the spectrum. We know that the rate of ATP production is the slowest with the beta oxidation of fat, but we know it also provides the greatest amount or the capacity to create ATP. And we saw that in the one slide where we had the table up top and the table on the bottom where it compared the one molecule of the glycolytic pathway and then the one molecule of the oxidative fat pathway. So just realize when you see a test question on this, it's easy to just go and try to answer real quick. But what they're really trying to have you do is just decipher this little chart. So it might be something that will benefit to have this chart up when you take a quiz or when you take an exam, because I can guarantee you this is on there. All right. Moving on to this. Moving on to this concept in terms of the inverse relationship that you have, that it's present in terms of the rate and total amount of ATP. So you can have a high rate of ATP production like you see in the phosphagen system, but the capacity to make ATP is going to be low, and that's the converse for the oxidative side. And as a result, the phosphagen energy system primarily supports ATP for high-intensity activities. We know that. The glycolytic system, moderate to high-intensity activities for short to medium. We know that. And the oxidative system for low-intensity activities of long duration. And we know that already, and we've already talked about that at length. But this passage in the book really reinforces what they're talking about in this table. And so if we get me out of the way here, tuck me up in the corner, when we have these slower, these shorter duration events, 0 to 6 seconds, 6 to 30, et cetera, we can classify that as very intense, and that's going to be primarily phosphagen system. If we go 30 seconds to 2 minutes, that's going to be heavy as they qualify it, and it's going to be fast glycolytic. And then when you get into 2 to 3 minutes, it becomes fast glycolytic and oxidative. That's that overlap we've talked about in terms of like when one energy system takes over. And then when we get to greater than 3 minutes, it becomes a little bit lower intensity. But again, I would challenge you to question somebody who runs cross country or runs 5,000 and track, and they will tell you the intensity is quite high, but that's the oxidative system. So the point I'm making here is when we look at these kind of juxtaposition, table 3.3 and table 3.4, it reinforces what they're talking about in the book in terms of the level of intensity of an event and what is a predominant system. And then it's the predominant system can have a high rate of ATP production, but it doesn't have the capacity to create a lot. Whereas it could have a low propensity to at a rate of ATP production, but it has a high propensity, to create ATP. So they're really trying to hit home here between these two tables, the concept of the inverse relationship that you see. I'm going to break off from this. I'm going to go to the final presentation. I'll be right back.